Here in this lecture, we are introducing the concept of multiple linear regression. So as in our univariate linear regression case, we have a response variable y. Unlike that case, we now have more than one predictor variables. So we have p predictors. And we label these as x1, x2, up to xp. And so the idea is these xi are being used collectively to predict the response y. And we will also have n observations. So we write this as n observations for the predictors. So we say xi1, xi2, up to xip, and so each one of these has two subscripts, I for the ith observation, and then the second subscript tells us which of the predictors it is. And so we have this for I going 1 to n, and in addition, we have a yi. So for each I, we have an observation of the predictor vector and the response variable. And as in our univariate case, our goal is again use of the predictors x1 to xp to predict that response y. And that is actually an estimation of the conditional expectation of y given those predictors, x1 to xp. And the model that we use is very similar to what we did in the univariate case. So recall, in the univariate case, we would say that the response, yi, was equal to some intercept, beta naught, plus beta 1 times xi plus epsilon I. That's what we did in our previous lecture. And now we extend this. So we will have a beta for each of the predictors. And we obtain this model here. So you see we still have yi, the response, equals beta naught, our intercept. But then we have plus beta 1 xi1, plus beta I xi2, up to beta p xip, plus our white noise term, epsilon I. And it is true that we can still think of each of these betas, this beta naught as an intercept and the rest of the betas as a slope type term. But the difference now is that beta, say j, is the partial derivative of this y with respect to xj. So each one of these betas is the slope of this when we restrict it to the partial derivative associated with xj. We typically also assume that our predictors are independent of our noise term, of the epsilon i's. The idea being we have some explanatory information coming from the predictor variables, and then all the other randomness that happens in the world for that ith observation is captured by this epsilon I in a way independent of the rest of the predictors. In this sense, this is a regression hyperplane. If we look at the case where p equals 2, it's actually a regression plane. You would have a scatter plot of points, and you would get a plane that best fits them. But for p bigger than 2, we are now in higher dimensional space than we can picture. But the idea is still the same. It is the best fitting. We want to obtain the best fitting hyperplane in that space. And the way we do that is as we did in the univariate case using the technique of least squares estimation. And so remember that the idea of least squares estimation was to sum over the square of the errors. And so in this case, the way we do that is we minimize over all possible beta naught, beta 1, up to beta p, the sum over all the observations, I goes from 1 to n, of, to get those errors, we would have the actual observed yi, so there's our observation, minus our predicted yi, and then square that difference. So here we have the observed response, and here we have the predicted response. And our predicted response comes from our hyperplane. And so in here, we have our beta naught plus beta 1 xi1 plus beta 2 xi2 up to beta p xip. And you can think of this as the vertical distance between that ith observed response and the corresponding point on the hyperplane that lies above the value for the predictors. So it's just a higher dimensional idea of what we did for the univariate case. And in this case, we also, again, have a quadratic optimization problem. And the first order conditions will be necessary and sufficient. So you would take the partial derivative with respect of this objective function with respect to each of these beta i's, set it to 0, and solve them simultaneously. We will actually look at how that's done a little bit later, and we obtain something called the normal equations. But for now, let's just recognize that we have this least squares problem, which gives us a solution because it's a convex quadratic problem, and that gives us this best fitting hyperplane. So this is the idea of multiple linear regression, and again, it's really just an extension of what we looked at in the univariate case.